real statistics, stuff that you're actually going to use in the future. Okay, we're going to start working with, rather than populations and these imaginary means of entire populations, standard deviations of entire populations, we're going to start actually working with samples. And you're almost universally going to be working with samples as you go on in the future, because it's just not practical to be able to survey an entire population. Anybody know of a situation where you survey an entire population? Once every 10 years, a census, right? That's almost the only time that you really get involved in actually surveying an entire population. So sampling is important to us, and the mechanics of sampling is particularly important to us. For instance, if I were to sample 100 students that go to school in this building, I'll randomly pick samples at various times of the day as they enter, and I told you that the average age of that sample of 100 students was 35 years old. Does that mean that the average age of the entire population of people that go to the school is 35? No? Well, do you think that the average age would be between 30 and 40? You think? Would that be reasonable for me to assume? If I did exactly that, took 100 people, right? It's hard to say, right? You don't know if that sample of 100, if you can trust that to give you a range for the actual population sample, you don't know whether you should assume, well, if it comes out 35 with 100 people, maybe I should assume it's 25 to 45 or something like that. Maybe I should assume it's 34, maybe 100 people is such a good sample that maybe I can assume that it's really like 33 to 37 or something like that, right? That's important to us. We have to know how well we can rely on the results of that sample, and that's really what we're going to get into. And once we know how to do that, we can compare one group to another group using samples. But until we know that, we really don't know what kind of precision these samples give us. Obviously, for the most part, you can say certain things about samples right off the bat. For instance, when you take a sample and you find a mean of that sample, that mean approximates the sample of the entire population. Bigger the sample is, the better the approximation. Take a small sample, could be a lot of error in that. Take a big sample, it's probably less error than there is in a small sample, right? Now what about the variability of the values? For instance, if I took a big sample and I took say I did that with 100 people, I took a mean, and then I did it again with 100 people, then again with 100 people, and I took all of those averages. Would you expect the variability of those means of the repeated samples to be as big as the variability as the population? No, you'd expect it to be very narrow, right? Because the population may be from 18 to 75. Right? But if you take a sample of that larger number of people, you would expect that each time you take a mean, you're not going to get all 18-year-olds, you're not going to get all 75-year-olds, but the means are going to be closer together. Another interesting thing is that the mean of that population is a fixed number. It's not a variable, it exists. There's only one number which represents the mean of that population, and you would only get that if you took everybody's age and divided by the size of the population. Okay, so that's a fixed number. Now you can say to yourself, okay, well, that's a fixed number. The variability, it varies quite a bit. You know, it can vary depending maybe on the sample size. Bigger sample size, less variability. Smaller sample, smaller variability. So we're going to test that right now. On Blackboard, under this session, you have a document. If you downloaded it before, you might want to re-download it. I made a couple of changes in it. But you have a document, a Word document, that we're going to do an exercise with. Okay? And we're going to work with an imaginary population of 100 people. And these are maybe test scores, maybe they're blood sugar levels or something like that, whatever they represent. They represent 100 values that have been measured. Okay? And this is the entire population. We're assuming the entire population is 100 people. We're going to, since it's small enough and we have some tools with us, we're going to calculate the mean and the standard deviation for the entire population. You have on Blackboard also an Excel file and an SPSS file. I'll leave it up to you to decide which of the two you want to use to calculate the mean and the standard deviation for the entire population. Okay, I'm going to do it while you guys give it a try also. Here's my Excel file. I'm going to say equals, let's see, equals average, parentheses, and I'm going to highlight all of these numbers, enter, and I got an average of 50 for this population, and the standard deviation of this population is 9. Okay, they may not be exactly that. I didn't format this, but I'm going to leave it at 50 and 9. That may be rounded off. I'm not sure. When you do it on yours, you might want to check to see if there's some more decimal places. But I'm going to stick with that for now. Okay, so nice round numbers, 50 and 9. And they're right, nice round numbers because that's not an accident. It took me hours to do that, okay? So it's not by accident. In fact, they're actually normally distributed. So, and that's a little trick you can do it with Excel. You can actually generate random numbers based on a normal distribution. Okay, so there's our population. Mean of 50, standard deviation of 9. Well, now we're going to imagine that we're researchers. And we're going to go out into this population. We don't know that. That's something that's unknown to us because we can't measure the whole population. We're going to go out into this population and we're randomly going to select 10 people, 9 people out of this population. I think that's the first exercise that I came up with. Let me see. Okay, yeah, sample size of 9. And the way we're going to do this, did you guys just discuss random samples in the lecture? I think you did, right? And you worked with, we mentioned a random number table. You have one of those on Blackboard that you can download. Okay, this is a random number table. This is an explanation of a random number table, or actually if I go far enough, there's a random number table. These numbers have been, through some method or other, maybe computer or something like that, these numbers are completely random, presumably. Okay, and there's many methods that they use to generate these kind of tables, but the sequence of these numbers is random so that I can start anywhere and I can use these as a direction for random numbers. Well, since we have a table which is rows and columns and there's 99 positions, I'm going to use 2 digits at a time here. Now I'm going to ask you guys to start anywhere you want on any page on this table. I'm going to start here. First number I got was 25. In other words, row 2, column 5. Okay, and I'm going to go to row 2, column 5, and I'm going to write that number down either on a piece of paper or, better yet, on Excel. Okay, next one is, let's not allow it to repeat. Okay, I happen to get a repeat there, so let's just, if a repeat, skip that. Okay, 2, 5. Next one is 5, 4. Okay, that's row 5, column 4. Next one is row 0, column 0. Next one is row 2, column 9. You do your own. Don't echo what I'm doing. Everybody's going to do a different one, right? So go ahead. Do it. I see people staring at me. Stare at the computer. Okay, so you guys got the idea what you're doing? Okay. Open this table. No, that's honest. That's okay. I don't mind that. Okay, we're going to open this table, and you're going to start from, you're going to pick a spot, start from anywhere, like that one's 8, 8. And you're going to find 9 numbers off of the original table that we have back here. This table, like 8, 8 would be row 8, column 8 would be the number 64. And then you would go back there, and wherever 8, 8, I lost it now. Wherever 8, 8 was, then you take the next 2 digits, row 4, column 4, next 2 digits, row 5, column 6, 4, 3, 6, 1, and you're going to use those to generate, in order to randomly select numbers, 9 numbers from that population. Okay? Okay, now you could say, oh, I'm going to blindly pick here and pick here and pick, but you're going to introduce some bias. If you're a right-hander, you're going to get more numbers on the right hand. You're left-hander, you might get more numbers on the left hand. You know, or maybe you have a tendency to pick out of the center. If you do it yourself, you're going to introduce some bias. If you use the table, you can depend on it, if we do a large enough sample, for it to be relatively unbiased or random. That's the point of using the table instead of just doing it ourselves. Okay, and what I'm going to do is I'm going to open a spreadsheet in Excel. I'm going to use the same one. Okay. Let me get a new page. I'll use this one. Okay, I'm going to use this one. And as you get it done, tell me the mean of the 9 numbers that you have. And tell me the standard deviation of those numbers. Actually, no, actually don't tell me the standard deviation. Just tell me the mean. Be good enough for now. Any volunteers yet? It's only 9 numbers. I'm getting desperate here. Basically what we're doing is we're recreating a scenario where you would be sampling a population. Okay, just give me the mean. Don't need the standard deviation, just the mean. And as soon as you get it, yell it out.
51.
Oh, thank you. Good work. Next.
And the standard deviation 6.
Yeah, don't worry about standard deviation. We're going to worry about that in a second. Just the means for now.
48.
48, thanks. Okay, good. Any more volunteers?
51.
51?
49.
49? Need a few more. What was that? I heard one. What was that? 49, that's okay. Don't matter if it's the same or not. It's random. We want to see what actually happens here.
48.
48. Next.
40.
40, good, okay. There's one that's a little bit of an outlier, but go ahead, yes. That's, hey, listen, that's going to happen. That's, remember, what we're examining here is what happens, really happens when you take samples. Anybody else? Let's give me a few more. 46. Okay. Okay. Speed her up a little. Remember, anybody anybody a Lucy fan? I Love Lucy fan? Remember the one with the candies? Speed her up a little, you know? Speed her up a little. 39, okay, wow. A couple of low numbers there. Keep going.
54.
54, good. Just one or two more.
51.
51, okay. One more.
47.
47. Okay, let's stop there. First thing I'm going to do is I'm going to say to myself, okay, look at the range of these. I got values as low as 40 or 39 and as high as 54, right? When we know the real population mean is really 50, right? I'm going to take the average of the means. The average of the means is 48. Well, it's the average, see, notice that 48, that's a bit closer than these extreme values here, isn't it? That's the average that we have of all these means. if I repeatedly take samples over and over again. If I take an infinite number of samples from this distribution, this population, an infinite number of samples of size 9, what do you think the average of all of the infinite number of samples would be? It'd be 50, right? It would be, but now we're taking a small group of samples. It happened to come out 5048 this time. Okay, I'm going to calculate the standard deviation. Okay, let's calculate standard deviation for all these repeated samples. Comes out to 4. Okay, was that bigger or smaller than the standard deviation for the population? Smaller. It was 9 before, right? So the distribution, the spread of these numbers is smaller than the spread of the entire population. So we said the population standard deviation was 9, right? Well, this is 4. I'm thinking 4, 3, or 4. What is 3 relative to 9? It's a third. It's also what? It's the square root of 9. We're going to find that the sample size, the standard deviation for repeated samples of size n is equal to the standard deviation of the population over the square root of the sample size. If I took enough samples, this would turn out to be 3. If I took a sample size, remember our standard deviation was at 9, right, for the population. If I took a sample size of 81, right, sample size of 81, what would be the standard deviation for repeated samples of size 81? 9 over the square root of the sample size, 81, 9. The standard deviation would be 1, because with a sample size of 81, you're going to get all your numbers are going to be much closer to the mean than this is. This is a valuable tool for us because it tells us a lot about the way these samples are distributed. Okay, let's take a look at what some of the things that we can do to make this a practical benefit for us. Okay. Okay. Okay, first we're going to look at a population. And before I do that, I'm going to track down my phone so I can keep track of the time. Okay, so we're going to look at something for a population. Forget about the sample, put the samples aside from, this is just kind of a refresher on how populations act. Okay, total cholesterol of a certain population is approximately normally distributed with a mean of 200 and a standard deviation of 20. What percent of the population is between 180 and 220? One standard deviation above, 68%, right? Okay, what percent is between 160 and 240? That's 2 standard deviations, 95%, right? Just a bit of review on there. Greater than 225 milligrams per deciliter. Let's see, 220. What's a z-score for 225? Let's see, it's 225 over 20, which is 1.25. Everybody okay with that? Right, it's 25 over the mean. Standard deviation is 20, 1.25. How do we figure out what area is greater than that? Well, we go to our table, our z-table, or you can do it in Excel if you have Excel handy, and a z-score of 1.201234 is 89.5%. But that 89.5% is this area from that z-score down. We said we wanted the area above it, so it'd be about 11%, right? 10.5 or 11%. Okay, so that's how we would do that. Okay, so now I'm going to move on from that, and that's how we dealt with the population. That's how we dealt when we knew mu, the mean of the population, and sigma, the standard deviation of the population. How often do we know that? Almost never. Now let's take a look. Well, it's true, right? We almost never know that, right? And it's nice that we did that for the first 4 weeks, but now we're telling you that that's not any use to you because you're never going to know that, right? Now we're going to deal with samples, and samples is what you're really going to be working with. Okay, let's see. Same population as above. Mean of 200, standard deviation of 20. Okay, you take a sample of size 25 from that population. What's the probability that the mean of the sample is between 196 and 204? Well, in order to figure out what the mean, we take a sample of size 25. right? And the mean of let's see, was probability sample. So we have the mean of 200, right? Okay, and standard deviation. So what would be, now we're looking at a new distribution before. Now, remember the distribution that we looked at before? The mean was 200, right? And the standard deviation, one standard deviation, this was 180, and so on and so forth. The standard deviation was equal to 20. Now this new distribution that we're looking at is we're looking at what if we took repeated samples, right? Because I want to know what's the probability of me getting a sample that's higher or lower than 200. Well, we know the mean's 200, so 50% chance of getting a sample below 200, 50% chance of getting above 200, like we got 54 and 51 and 52 and 40 and so on and so forth. Well, our new distribution is going to look narrower. It's going to look narrower, but it's also going to be normal. These are the samples, the scores that you were giving to me. Now, you would expect you take enough samples, the mean is going to be the same if you take enough of them, 200. But the standard deviation, I'm going to put SE because I'm not dealing with the population anymore. The standard deviation or standard error, we give it a new name to indicate that it's the spread of the repeated samples. That standard error is going to be equal to the standard deviation over the square root of the size of the sample that you're taking. Okay, so let's see. The standard deviation was 20. The sample is 25. The square root of 25 is 5. So the standard error, or the standard deviation of these means, of the means of the samples, is equal to 4. So 196 and 204 is how many standard errors away from 200? 1. So 68% of those samples will come up between those two numbers if we take enough samples. And 192 and 208, that's 2 standard errors. 95% of the samples are going to come up between those two. Okay, so I'm going to move on a little bit. Oop. I don't want to do that. Come on, let me move. There's a way to make it stop doing that. Okay, I'll close and clear. Just makes it go away, but it's okay. I don't need it anyway. Okay, sample size 100. Okay, let's see. Okay, I'm going to go to a sample size of 20. We're still in our sample size of 25. Okay, if we take a sample size of 25 from this population, within what range would we expect 95% of the sample means to fall? Okay, what am I saying there? I'm saying that we're taking a sample of size 25, right? And I know the mean of the population is 200. I know it's around 200. And I'm saying to myself, okay, the standard deviation of the population is 20. Now, 95% of the results I would expect to be within 2 standard deviations of that mean. Just the inverse of what I was doing before, right? So in other words, I can say to myself, well, gee, if I took repeated samples and I would find that 95% of the time, if the sample size was 25 in this situation with this particular population, 95% of the time I'd get a result between 192, was it? 192 and 190 and 208, right? Two standard deviations below, 2 standard deviations above. Now, another way of looking at that is saying that if you take a sample and you look at that sample, and that sample is approximating the mean of the population. That's the whole point of taking the sample, is to estimate the mean of the population. Another way to look at that is to try and figure out, well, I'm going to estimate the population standard deviation based on what I know. And I'm going to say to myself, well, I'm going to take 2 standard deviations below that mean that I got and 2 standard deviations above that mean, and let's say to myself, you know, I'm 95% sure that other samples will fall in that range, but that the real population range is within that range. Can I ever be sure that the real population is within that range? No, because there's so much chance involved. But it's good enough for us to know how certain we are. Remember before we were just talking about How like if I told you we took a sample of a certain size and it came out to be average age is 35, do we know if the real population is 30 or 40, or is it, should I assume a range of wider than that or narrower than that? This is a way for us to judge that. We could say to ourselves, based on knowing the population standard deviation and the sample size, we take a sample and we can say to ourselves, we're 95% sure that the real population average is going to be within 2 standard errors because we're dealing with a sample, right? Within 2 standard errors of the result of our sample, right? What's that called? Did that come up in the lecture? Right, we're 95% confident, right, exactly. That's the 95% confidence interval. And you see that in papers all the time. You read an abstract that says that the average blood lead level for this group of kids was 10 micrograms per deciliter with a 95% confidence interval of 8.3 to 13.7, right? Why do you need that? Because now, when they tell you that the average was 10.1, they're also telling you that tells you you're 95% sure that the entire population of kids within that group, that we're 95% sure that the real population mean is between 8 and 13. So now, if I compare it to another population where I'm 95% sure that the other population is between 15 and 25, I know that I'm 95% sure that the real population means are different for those two populations. If there's overlap between those confidence intervals, I'm not sure that they're really different anymore, right? So this is important to us. This is the way we're going to compare groups. Okay, we're really interested in the mechanics of these things. Okay, clear that. Okay. Now, I put some exercises in here that we can do together and that you guys can continue on your own. For instance, you sample 100 bottles of detergent, a brand A, and find that on average, each bottle is sufficient for 57 loads. You know that the standard deviation for the entire populations of bottles is 5 loads per bottle. A little bit tricky there, right? Why would I know the standard deviation for the entire population? Sometimes you have an estimate of it because some other study did a very large sample or something like that. But the reason why I'm doing that is because up until this moment now, we're assuming that the standard error is equal to sigma over the square root of n. Right? Standard error is something that's based on a sample or repeated samples. Sigma is the population standard deviation. When we move on a little further, we're going to actually be using the sample to estimate this as well. It's going to introduce an extra error for us because the standard deviation of a small sample may not be, just like the mean could be a little variable, the standard deviation, if you base it on a small sample and extrapolate that to being the standard deviation of the entire population, that introduces a little more error. Later on, we're going to learn something about something called a t-test, which is going to deal with that. We're going to have to take that into account because we're not really sure what that is. But for the moment, we're going to assume that we know that so that we can get past at least this part of it. How many of you heard of the t-test before? How many of you could run one if you had to right now? Okay, a smaller sample than have heard of it. Okay, good. That's what I suspected. That's a good thing. That means we're going to learn something. Right? Okay, so let's see. Let's see, 50, so you take a sample of 100 bottles of detergent, and you know that the standard deviation for the entire population is 5 loads per bottle. Okay, is 57, is that mu or x bar? X bar, right? That's a statistic because that's the sample average. 5 is sigma or standard deviation? Right? That's something came from that's the entire population. So that's sigma. That's a parameter. Okay, that's just the way they gave us the information. Won't come up very often. As I said later on as we go on, we're going to look at other ways to deal with this. Calculate the standard error for repeated samples from this population of size 100. What's that equal to? Sigma over the square root of the sample size. Okay, so what's the standard error for this for samples of this size? 5 divided by the square root of, what was it, 100 sample size? Okay, and what is that? That's 10, that's 0.5, right? Okay, calculate the 95% confidence interval for the population based on this sample. Okay, so now, what was the mean that we got from this sample? 57, right? Okay, now, we want to go 2 standard deviations below, 2 standard errors below 57 and 2 standard errors above 57. How much is the standard error? 1/2, right? 5 divided by square root of 100, which is 10, right, is 1/2. 2 standard errors would be 1. So we want to go 5 below 57 and 5 above 57. 2 times half, or 1, plus or minus 1. So what's our 95% confidence interval? It's 56 to 58. We're 95% sure the true average number of washes that you can get out per, loads that you can get out per bottle of this detergent is between 56 and 58. Okay, comfortable? Yes.
Did you get the one, sorry, going from the...
First thing I did was, we took a sample of size 100, and we got an average of 57. I want to know what kind of confidence can I have in that number, that average 57, in relation to the true population, the true mean of every bottle of that detergent. Okay, so I need to get a handle on what the variability is for repeated samples of size 100. That's where I need the standard error instead of the standard deviation. Now, we knew that the standard deviation, we were told standard deviation for the entire production run, for every, if you looked at the entire population, was equal to 5. The sample size here is 100. So the standard error is 5 divided by the square root of 100, which is 10. 5 divided by 10 is 1/2. Okay, so I want 2 standard errors on either side for, using the empirical formula. So that was 57 plus or minus 1. Okay. Yeah, so now let's say I told you the sample size was only 25. That would be 5 over the square root of 5, 25, which is 5. So the standard error would be 1. So our 95% confidence interval would be 57 plus or minus 2, right? So 2 below, 2 above. Okay, so it would be 55 to 58. If I took a sample of 9, sample size of 9, that would be 3. 5 over 3 is going to be 1 2/3, right? 2 standard deviations is going to be 2 1/3. I got that right? Right, 2 1/3, so that would be so on and so forth. Okay, sample size impacts that. What happens if I want to, let's see, what's a good way to put this? Let's see. If I want a higher level of, let's say I was willing to, if I were to look at this another way, and I was to say to you, I'm only going to look at 1 standard deviation below and above the mean. So I'm going to say 57 plus or minus 1/2 would be 56.5 and 50, excuse me. Standard deviation. No, I'm not going to go there for now. Let me skip that. Okay, I'm not going to go there for now. I'll confuse things. Okay, so I'm going to move on to the next part. Actually, no, I don't want to move on to the next part yet. 95% population based on this sample. Okay, if company brand B is known to produce a product that washes 95 loads per bottle, can you say with any certainty that brand A goes further than brand B? Or the other way around? Oh, you know what it is? I thought that's supposed to be 55 loads per bottle. Okay, brand B does 55 loads per bottle. Okay, you would be 95% sure that brand A does more than brand B does, because your 95% confidence interval is 56 to 58, right? But if we had only done a sample size of 25, you wouldn't be able to say that, because you wouldn't be sure enough of the population, of the true population average for the one that you sampled, to be able to say that it's different than 55. Okay? Let me close ink layer. Okay, let's take a look at this one. Okay, suppose we want to know the true population. Oh, there's proportions. Let me see if I can get away from it. But did you guys talk about proportions while you were in lecture? Didn't get to that, right? Okay, I want to avoid that for now. Just so that we, since it's up there, I don't want to leave it just hanging there. You know, for instance, that many of the studies that we do are surveys that involve proportions. In other words, they have, you're looking for a prevalence, or you're looking for, whether something improves or doesn't improve, illness, no illness, so on and so forth. A lot of things are expressed as proportions rather than strictly as numbers. For instance, we might know a population that has a prevalence of a certain disease of 20%, right? So the prevalence is equal to 0.20, right? Now, we may want to compare that to another population. Let's say we go out and we're not going to sample the entire population. We're going to sample a small group from that population, say 100 people. Okay, so now we sample that population of 100 people. And and now we find out that the prevalence in that population is 18%. Well, now, problem here is that the sample prevalence was 18%, right? But we don't know what the entire population prevalence was for that disease. So we need to know, just like we did before, we need to know how confident can we be in that number, 0.18, 18%. So we don't want really a single number. It's nice to know that. We want a range. We want that 95% confidence interval for proportions, just like we would want it for a regular number, a numeric variable, a scalar variable. We're going to be able to do that. I'm not going to do it now since we didn't cover it in lecture yet, but just keep in mind that we're going to be able to calculate, because if we took a sample even from this population, we're not going to get 20% every time. Sometimes we're going to get less, sometimes we're going to get more. What determines whether we get less or more if we really randomly sample and they're independent samples? Well, chance determines that. Right? And based on the prevalence, we can calculate a standard error for this proportion, just like we can for scalar numbers or regular numbers and stuff like that. We're going to deal with that later on. But keep in mind that everything we do with regular numbers, we're going to be able to do with proportions as well, and create a confidence interval for these kind of studies as well. Okay, let's see if we got something else we can close ink layer. Okay, let's see. Okay, well this is an example. It's based on actual numbers that we might be working with. Okay, and let's say in this particular case, this is a random sample, right? All independent samples. We randomly sampled a particular maybe we use a random sample of bottles of this detergent, and this is the number of loads we got out of this random sample of bottles. We also are making the assumption that the distribution is approximately normally distributed. In other words, that there isn't some bias in here, that some of the bottles were filled more than others and we picked out from one end of the group, or we picked the heavier ones or something like that. So they're normally distributed and they're randomly sampled. Calculate the mean load of bottles, mean number of loads per bottle. Anybody want to calculate that for me using Excel? And calculate the standard deviation too. Okay, you're going to calculate the mean and the standard deviation. X bar and standard deviation. X bar is going to approximate the mean, and standard deviation is going to approximate sigma. Anybody got the mean? Am I being unreasonable here? 92.7? Okay, and standard deviation?
Five.
5.6? Okay. Now, remember what we did before? If I wanted to know what's the 95% confidence interval for the true average number of loads you could do with this particular brand of detergent, right? Well, I got the mean, and I would want to know what the standard error for these repeated samples is, right? And the standard error is going to be equal to the standard deviation over the square root of the sample size. Problem is I don't know that, right? I don't know what that is, right? And the only thing I can use to approximate that is the same thing I did with the mean, which is to use the standard deviation. Okay, that's 5.6. Square root is, how big is the sample size? 10 or 9? I'm going to make believe it's 9. I'm going to make believe it's 9 anyway, so I can divide by 3. Okay, so that's going to be equal to, I'm going to round it off and say that it's equal to 2. Okay, that's really nice, except I cheated, right? I used the standard deviation of the sample to approximate the standard deviation of population. It does approximate it, but it's not exactly the same. I've added an extra layer of uncertainty. So when I calculate my confidence interval, it's going to be 92.7 plus or minus 2 standard errors, right? Well, instead of 2 standard errors, I'm going to increase that number. That number, and I'm going to increase that number based on the sample size. If it's a small sample, I may say make that 2.5 times the standard error to make up for that error. Remember, wider interval, right, means a larger level of confidence. Narrow interval means less level of confidence, right? So 2.5 times the standard error. If it's a bigger sample, it might be 2.3. If it was an infinitely large sample, it would be what? It would be 2, because that would be the same as the mean, right? It would be the same as the population. If you repeatedly sample enough, it'd be the same as the population. Second lie that's in here, okay? Remember the other lie that we've been telling you up until this point, or I've been telling you up until this point, is that 95% confidence interval is the mean plus or minus 2 times the standard error. Okay, based on, let's say it's based on sigma. It's genuinely the standard error. That's 2 was based on what? Where did we get that? The empirical rule. Is it really 2, that number, that represents 95% of the population? Let's take a look at this. Which number, 95% of the population, 95% of the population would mean that 2.5% is left at the end, right? Okay, so that would leave 0.975 is what I'm after, right? 0.975 is below this point. There it is right there, right? So the point at which the z-score, which means that 2.5% is above and the corollary is down below, right, is actually this number here, which is a z-score of 1.96, right? So when I do my standard error, I really shouldn't be using 2, I should be using 1.96. The empirical formula is just an approximation, right? The real number that we want for that confidence interval is 1.96. Okay, so this is really cool. We now have a mechanism that we can use to, when we take a sample, have an understanding of how accurate that sample is in terms of estimating the true population mean. Okay, and that's going to be enormously valuable to us in the future. Okay, so that's it for now. Is there questions on this, or questions? Do you want to hit a quick question on the exam?